Thank you very much for inviting me. It's a very nice workshop. I'm learning a lot. So what I'd like to do today is to review briefly what we have done last 10 years or so about the deformation in the deep mantle, not only lower mantle, but the transition zone. As a result of collaboration with many people listed over here, let me start with some of the geodynamic questions related to rheological properties to set the goals. Okay. As we have seen several times yesterday, the seismologists show that subducting slabs that are very cold, so therefore you must expect very strong, supposedly strong slabs are deformed in certain regions, particularly in transition zone. And then you should ask, why do they deform at all? Because if you just applied a simplistic temperature-sensitive rheology, they wouldn't, because it's so cold. And that's one question. So we like to understand why they deform in the deep mantle. And as also we saw this several times, the big question of whole mantle circulation, particularly in relation to geochemical reservoirs. Why do they survive so long time? And another question, briefly, I'm going to touch upon is the business of water circulation. Some people invoked the water-sensitive rheology to regulate water content, but that is based on knowledge on olivine. And the question you should ask is, do other minerals, rheology depends on the water, and I'm going to tell you my view, based on our results, is that the lower mantle minerals, probably water doesn't do anything about deformation. Seismic tomography shows some cold slabs deform in the transition zone. How does a cold slab deform? And I'm going to discuss the key parameter to key issues in relation to answer this question is perhaps grain size. Then geochemical reservoirs. I don't think we have any clear answer for it, but some of the nature of details of deformation might be related to this question. For instance, if the deformation in certain area has a tendency for strong localization, then even the whole mantle convex, maybe very small fraction of material is circulating, and large part might be just sitting. So that's the interesting question. And as I said earlier, water business is a big question. And so far, all geodynamic modeling about water circulation, like a water rheology feedback, those modeling is based on our knowledge on olivine, and not the lower mantle minerals. And I would argue the situation for lower mantle minerals is very different in respect to the water business. So to answer those questions, particularly I try to answer those questions, you really need laboratory experiments at high pressure temperature conditions. It's really tough. I spent more than 10 years to develop new technology, and now we are getting a little bit of the data, but not complete. So I have no confidence that our results can be applied to the Earth's interior, but I'm going to show you some of the results which we got so far. Before I present my own results, let me review briefly the kind of history of deformation studies. One of the first person to do a deformation experiment was David Griggs 8 years ago. Actually, he developed the new apparatus when he was 25 years old, and then he wrote 2 review papers in that year, 25 years old. One is a review on mantle convection, and one is a review paper on the rock deformation. It's an amazing guy. And then Patterson came sometime later to develop extremely high sensitivity, nice apparatus, but operates only at very low pressures, 10 kilometers deep in the interior. And then the Chris Getze, brilliant mineral physicist, did the first experiments on very high pressure deformation, but at room temperature. And then the Harry Green developed a little bit, and then Singh developed the theory of the X-ray stress measurements, which is critical for extending the conventional technology to synchrotron technology. And then Don Widener here, is main contributor to synchrotron deformation technology. Then we followed up Don's suggestions. So those are key developments. And then early this year, we published the first paper on deformation of the lower mantle after 10 years effort. Okay. So the conditions for deformation experiments in the laboratory, Griggs developed some technology to up to 2 or 3 GPa in terms of depths, 100 kilometers or so. And then Patterson developed really nice apparatus, but it's only 10 kilometer depths. Okay, so that's compared to the whole range of conditions, upper mantle, transition zone, and lower mantle, very narrow area. And so that's a really serious limitation because pressure has enormous effect on the many physical properties, including deformation. So we must extend those conditions for the experimental studies and the deformation to much higher pressure and temperature. So as I said earlier, I started this, let's see, the 1995, so almost 20 years ago, to extend the temperature pressure range for quantitative rheological studies. Then right now, we have extended those conditions to 27 or 8 GPa and 2,200 Kelvin. So now conditions are a little bit to the lower mantle. Okay, so to answer those questions, what we need is the deformation experiments at higher P, and then I'm going to discuss briefly. Deformation experiments must be conducted under the appropriate conditions where deformation mechanisms in a laboratory are perhaps similar to what's going on in Earth's interior. That's a big question, and I do not have any clear answer yet as to either our experimental results are applicable to the Earth's interior. But I'm going to discuss this issue because it's so serious. Because if the mechanisms are very different between lab and Earth, you cannot extrapolate those results. That's a really challenging issue in terms of very specific to the studies on plastic deformation. And so to extend the pressure and temperature conditions, you really need to design new apparatus because if you purchase apparatus, if you got money, you can purchase it, but those apparatus works only 0.3 GPa. Okay. So I extended 0.3 to 30, so 100 times higher pressure. So this is the apparatus which I designed. Essentially, this is the apparatus in which you squeeze your specimen by 2 anvils, like a diamond anvil. It's not diamond, but anvil. Uniaxial compression, and then you have to put lots of stuff here. There are heater and your sample and insulation material, etc., etc. Then you generate high pressure temperature here, and then you rotate one part relative to another by motor, and then slowly you do the torsion shearing test. Okay, the reason I chose torsion is in terms of torsion experiments, support for anvils is almost exactly the same as static experiments, so that you can go to much higher pressure in comparison to another technique, which you have a moving piston going through some space. In this case, there is a very high potential for failure. So that's number one. So number two, by torsion test, at least theoretically, you could go to really high strain. In practice, high strain is challenging, so the largest strain we have been under deep mantle condition is 300%, but that's still pretty large. So to do experiments under those high pressure conditions, you cannot use conventional technique or load cell measuring stress, etc., etc. You must use the in situ X-ray technology, like a synchrotron radiation facility. In this case, the particles accelerated, and the particle emit X-ray. Very intense X-ray, and using X-ray, as I'm going to show you, you can determine stress and strain. To do those experiments, you need to work with the students, and well, sometimes if you want to, wait a minute, yeah, your cat. Yeah, cat can help you to accelerate the particles. And then, all right. So the key points in the design of high pressure experiments, yeah, you must go to high pressure. That's easy, but you must also go to high temperatures because temperature matters. Low temperature and high temperature deformation mechanisms are completely different. And also, you must have a controlled way of generating strain rate or stress by just motor. And then it would be nice to have a large strain, and then that's why I chose the torsion design. And then another important part is how do you measure the stress and strain? So those are in situ measurements using X-ray. I'm going to show you in a few minutes. So to satisfy those conditions, I chose a torsion test. As I said earlier, good support for high pressure. You just rotate. So the old geometry of supporting anvils by some material doesn't change when you rotate. Okay? So this is a good, good support, secure to go to higher pressure, and it could go to large strain. And yeah, okay. So compared to those new technology, the classic apparatus, like Griggs or Patterson, you have your specimen and set into the high pressure temperature conditions. Then you apply load from the external actuator, and you measure the load. And then this is the stress measurements. And strain is also measured by external gauge to measure the displacement of two top and bottom parts. And the Patterson is the same thing. Load cell is inside, so therefore it's high accuracy. However, the apparatus can go only to 0.3 GPa. Yeah, so the concept of a classic deformation apparatus is sample is located in sample chamber, and then actuator apply the load to deform your sample, and then you measure the load on the outside of a load cell. If you go to the really high pressure environment, you cannot put any load cell inside of the sample chamber. So the measuring the stress and strain must be done by a completely different technique. Okay? So the synchrotron facility, high intensity X-ray, you can go to the really high pressure and temperature and monitor what's going on in your sample using a high intensity X-ray. X-ray does quite a few things. One is by X-ray you can measure the volume of your sample, and then using equation of state you can estimate pressure and temperature in situ rather than estimating sum couple. No, you don't need any sum couple. So you just measure the volume, and then you can determine pressure and temperature. And using X-ray, you can estimate both stress and strain. You need some theory to do that, but by using X-ray imaging, you measure the strain, and the X-ray diffraction, you estimate the stress. Another big advantage, which you took as an advantage, is by using X-ray, if you have two different materials inside of your specimen, you can determine the rheology of two materials separately. This you can't do it with the conventional apparatus. All you measure is macroscopic average stress. But with X-ray, if you have a mineral A and B, like bridgemanite and MgFeO, we are able to determine the strength of two minerals so that you can really precisely constrain the rheological contrast. So that is a very unique advantage of synchrotron facility. So the X-ray measurements of the stress strain, you put your equipment into the synchrotron facility, and then X-ray goes from the beam line, goes through your specimen, and then the X-ray does two things. One is we collect just the image, like a medical X-ray, okay? And the image tells you something about the shape of your sample, so from which you can determine the strain. And we collect diffracted X-rays as the function of orientations from which you can estimate stress. And this is the strain measurements. You have a specimen, and you can see the marker. And then from the rotation of the marker, you can determine strain rate. And by X-ray diffraction, you can determine stress. If you took X-ray diffraction as a function of various angles, before you apply the rotation, of course, at various angles, lattice spacings is a constant, and whatever orientation you measured, always the same thing, like a 2.02 angstrom, etc., etc. However, when you start rotation, symmetry is broken. And then this changed to sinusoidal, the variation of lattice strain, then from which you can estimate stress. So this is a way to measure both stress and strain in situ, okay, rather than the measuring stress by load cell or strain by displacement of something. No, this is the in situ measurements. This is remarkable because one of the fascinating things about doing those experiments is during experiment you can see your sample. Wow, my sample is rotating. This is fantastic. And then you can determine the stress and then pressure and temperature. We have applied RDA, rotational Drickham apparatus, to determine various rheological properties. First, we determined the pressure effects on deformation of olivine, because this was a very controversial issue. Like 10 years ago, activation volume reported ranges from 0 to 40. And 0 to 40 makes a huge difference in viscosity of the bottom of the upper mantle by like 20 orders of magnitude. And so we determined the activation volume. And then we conducted deformation experiments on some of the transition zone minerals, ozolite, ringotite, and then finally, we did the experiments on the lower mantle conditions. And the first results on the olivine, simply we deformed olivine aggregate at various pressures and temperatures and then determined the pressure effects. Briefly, the pressure effects are very large. So those are results we got, and then if you fit our results as a function of pressure and this is the strength, activation volume turns out to be around 15 to 20 cubic centimeter per mole. So the bottom line is the pressure effects is very large. And the pressure effects are very large, both in the power law dislocation creep regime, this is like a high temperature deformation mechanism, as well as the low temperature Pios regime. Pios regime pressure effects are also very large. So those are findings we got based on those experiments. And we also performed various experiments on the transition zone minerals. This is a paper by Robert Farah et al., published last year. And we collected lots of data, plus the rheological data, as well as the microstructure observations. And then we came up with the inferred deformation regimes corresponding to our experimental conditions. Those are over here, and then plotted against the roughly estimated deformation mechanism map. So the conclusion from this work, based on other work also in my lab, is that the conditions of deformation in a typical laboratory experiments are sometimes in the high temperature dislocation creep regime, and if grain size is small, sometimes it goes to diffusion creep regime, and if the temperature is low, you may go to the Pios regime. So the conditions are so close to the mechanism boundary, so you must very carefully pay attention to analyze the data to come up with some flow law. So the transition zone minerals main conclusions are that when you compare the strength of transition zone with olivine at given similar pressure and temperatures, the strength is not so different. But the most important conclusion perhaps is the deformation conditions are so close to the boundary between dislocation and diffusion creep regime. Very simple implication is that if this is the case, then if you have a mechanism of the grain size reduction, you could get a very large viscosity reduction. So this is the one conclusion that you can get from this analysis. And when you look at the deformation of the slabs in the transition zone, because of very high pressure effects on both the parallel creep and pulse, the low pressure results cannot be extrapolated to the discussion of the deformation of the slabs. If the pressure is 20 GPa, without invoking grain size reduction, slab would be so strong that you wouldn't be able to deform it. So only way, in my view, to deform slab is to introduce something additional mechanism, such as the grain size reduction. And to characterize grain size reduction, my student is working on the experimental work to find out what controlled grain size. And so we do experiments to see, we put our specimen of olivine to a Woolsey stability field at various pressure temperature conditions to see what kind of transformation microstructure you observe. The main conclusion is that when you do transformation experiments at higher temperatures, you tend to see much larger grain size than the conditions at lower temperatures. If you do transformation at low temperature, grain size is extremely small. So the temperature effect is so large that temperature at which transformation occurs is very important in controlling grain size. And so if slab is low temperature, grain size is so small, slab becomes very weak. Imagine grain size change from millimeter to micron, then viscosity would change about 10 orders of magnitude. Okay, so this is a huge effect. So the last, I'd like to briefly mention how we did the first deformation experiment to the lower mantle conditions. Extending conditions to lower mantle, I tried several times without success, but eventually we realized that there's a pressure gradient inside of this sample chamber, so we put small sample, and then we were able to deform a mixture of bridgmanite and MgFeO to a large strain of about 100%. And then, as I mentioned to you earlier, if you have two minerals, you have two volumes, okay? So therefore, by measuring volume, you can explain this volume by combination of certain temperature and pressure, one line. If you have two minerals, you have another data of volume, so that the experimental observation must satisfy another line. So by imposing both conditions must be met, you can determine the pressure and temperature. So in this case, the pressure was 27 GPa, and the temperature was 2100 K. And then we are able to determine strengths of each phase, namely bridgmanite and MgO. And then it turns out bridgmanite is substantially stronger than MgO under those conditions. And you can see some hint of rheological weakening. And the main point is that if you have a 70% of very strong material mixed with 20 or 30% of weak material, at least theoretically, you can speculate that there might be some process of shear weakening. Okay? And then this is the deformation microstructure. This is the before deformation, most of isotropic structure, but after torsion, you can see substantial amount of strain in your sample. And then you might speculate that if the shear concentration of deformation occurs in the lower, weaker phase, you might expect the deformation might be very much localized. This is the potential explanation for geochemical reservoir, why they survive so much. And then this might be able to explain the lack of seismic anisotropy in the majority of the lower mantle. So briefly, I want to show you some experimental results to tell you that at least in this mineral, MgFeO, water probably doesn't play any role in the rheology or diffusion. Main reason is, in olivine, if you look at the defects, hydrogen-related defects has much higher populations than the other defects caused by ferric iron. But in MgFeO, ferric iron is much more dominant compared to hydrogen. So therefore, hydrogen plays very little role. So the water weakening may not occur in the lower mantle. So to summarize, the quantitative deformation experiments have been done up to 27.8 GPa. The first results on the lower mantle deformation were obtained. In the transition zone, the deformation experiments were conducted to pretty wide range of conditions, showing that deformation conditions in the laboratory are very close to the boundary between the diffusion and dislocation creep. Then if you can extrapolate using semi-quantitative results, you can also speculate that the grain size reduction plays a very important role, in the, particularly under the lower temperature conditions. And in terms of the water, available experimental results and other observations, in my opinion, strongly suggest that the water weakening effect does not occur in the lower mantle. This has a potentially very important implication for water circulation. And then for the future, yes, of course, those are very preliminary results. You must extend the various deformation regimes, and you must demonstrate water has effects on deformation or not by direct deformation experiments under controlled water content. And of course, we are working on this, but the other practically very important application is to understand the anisotropic microstructure evolution during those deformation, which we can do and collaborate with Patrick Corday to characterize our specimens in more quantitative fashion. Thank you very much.